Okay. Thanks everyone for being so prompt and joining our webinar. We're here today to launch the ISEC tool. We are joined by Jeff Rissman and Nick Save, who are leading authors on this. They are going to walk everyone through a demonstration of the tool, talk through some of its top-line findings, and then we're going to open up to Q&A at the end. A few notes here. This is being recorded. You will get an email after the recording, after the webinar with the recording, a link to the presentation, as well as some other key links for this report. We have a Q&A function should have a Q&A function at the bottom of the screen, as well as a chat function. Please put all of your questions there. As I said, we'll certainly make sure to have time to go through everything. With that, I'll hand it over to Nick to get started.
Hi, everybody. I'm Nick Save. I've been with Energy Innovation for a little over a year as a policy analyst in the industry team with Jeff, who's our senior director. And today we're really happy to share our industrial zero emissions calculators. We think it'll be a great tool for you to integrate into your own workflows and gain an understanding of the scale of the resource issues and the solutions to industrial decarbonization and how best to strategize that across approaches. So Jeff, can you? And go to the next. So we've built the calculator because we know that the resource demands to decarbonize industry across nations are just not being sufficiently considered. And they're naturally of a scale and complexity that leave us with a daunting challenge of how to conceptualize those resource needs. So we wanted to build an intuitive and easy to use tool that allows people to readily visualize those resource demands and to explore the ramifications of different industrial decarbonization strategies, even ones that they can customize in detail themselves if they want to. When we were thinking through the design, we decided that we wanted something to sufficiently characterize the impacts of different decarbonization solutions. We didn't want to just stop at the electricity demands on the grid. We wanted to look at land use, emissions, and other resource implications as well to gain a multifaceted and nuanced view of the challenges ahead. We wanted to cover major geographic regions while being able to zoom out to a global view as well. And as I mentioned, we wanted people to be able to customize their solutions to industrial decarbonization and envision what their own preferences and what the best road forward to zero emissions would look like. Can we go to the next? So in the tool, visitors can decide on their region, choosing from the US, China, India, EU, and the world. You can compare custom scenarios against a number of presets that lean heavily on specific strategies like direct electrification or clean hydrogen. You can choose whether to include non-manufacturing areas that are considered part of industry by the AEO, including mining, construction, agriculture, and so forth, whether bioenergy use is displaced by zero carbon alternatives initially, or whether it should remain, and whether the calculator should displace existing use of purchased heat with zero carbon alternatives. We can also input our assumptions projecting how energy efficiency and material efficiency might improve in the coming years. For non-heat uses of thermal fuels, we can decide on the degree to which it's electrified. Primarily, one can think of this as displacement of fossil fuel engines with electric motors. And you can define the extent and mix of decarbonization solutions for heat supplied at different temperature levels. There are naturally different technologies for electrifying low, medium, and high temperature heat. We actually pull the industrial energy use out for each country by each industrial sector, for example, steel making or cement making, then break it down by the degree to which those particular sectors rely on different mixes of different temperature levels. Different stages of production actually have different demands. We take that into account. So we're mindful of how this changes the industrial sector's viable path to decarbonization, depending on where you are in the world and what industries these regions focus on, including the fuel sources that different countries rely on. Next slide, please. You can also define the methods of forming chemical feedstocks as well as their carbon sources. You can choose from hydrogen direct reduced iron and electrolysis methods to decarbonize iron and steel, and can define the exact mix of energy sources that are providing zero carbon electricity to the grid. Next slide. So we are incorporating 53 different data sources. All of these are public. They're carefully cited in the tool. You can sift through them and see where everything comes from and how the math works. The most significant data suppliers that we have include the EIA for the United States, China's National Bureau of Statistics for China, EU Commission, European Commission Joint Research Center for the EU, NITI Aayog's India Energy Security Scenarios for India, and the IEA for the world. Next slide. And as far as built-in scenarios go, they really hone in and focus on if we were to rely heavily on certain strategies to decarbonize the industrial sector, what are the ramifications of those? So we have one that focuses on direct electrification, one on green hydrogen, one on bioenergy, one on fossil CCS, a mixed scenario that is balanced across those, and then of course you can customize as much as you would like. Next slide. So there are three ways to explore the data. The main tool that offers full customization, as well as those built-in scenarios where you can see how all the sausage is made and the math works, is the Excel tool, still built to be very intuitive. But we also have a web app. You can see a screenshot on the right, and that offers a very easy interactive interface, describes the data for each region, walks you through what the results are, but offers only limited customization. And thirdly, we have a full accompanying report, and that really goes into depth on the tool's features and design, and analyzes our findings in the US context and describes what the implications are for decarbonization of the nation's industrial sector. So Jeff is going to go into the details of those findings for US industry.
Thanks so much, Nick. So for those who don't know me, I'm the Senior Director of the Industry Program here and co-author of this tool and this study along with Nick. And for my half, I'll walk through some of the key findings we have to share with you before we open it up to Q&A. So first, I wanted to show you this. This is industrial sector non-feedstock energy use. So this is the energy being consumed for heat and power. And in a way, this is the first two slides that just define the scenarios, show you what sort of what's in them. You can see that historically, in all the graphs I show, historical in the most recent available year will be on the left, and then the different scenarios will be on the right, excluding custom, which you would build in the Excel tool. So high direct electrification for non-feedstock purposes uses electricity as much as possible. These are set to preserve BAU bioenergy use, which is primarily in the pulp and paper and wood products industries, and a little bit in agriculture too for the non-manufacturing industries. So high green hydrogen uses a lot of hydrogen combustion, green hydrogen combustion, though it still does use electricity, both where for historical use and some low temperature heating. High bioenergy leans heavily into that strategy, bioenergy combustion, biomass primarily. Fossil CCS is using fossil fuels with CCS, and mixed is balanced. I'll also take the moment here to switch to the web tool for a moment. So I've switched to the web browser. You can see the same scenarios set up here. This is available through our website, and you can choose whichever region you want in this drop-down menu. So here's China, Europe, etc. And then you can toggle certain assumptions, whether or not you're including on manufacturing industries, whether you're displacing BAU bioenergy use. You can see the effect of that. For purchased steam, we need to look at a region that has steam in it, Europe, say, and then for any region, you can apply a 25% energy efficiency and or a 15% material efficiency. And you can switch between different graphs using this menu. The caption down here will update depending on what graph you're looking at and what settings you've checked when it has numbers in there. For ease of presentation, I'm going to be showing you these graphs in Excel PowerPoint slides, but just remember that they're there in the web tool as well. So I'm going to move on to feedstock use. So feedstocks are fossil fuels that are not burned for energy, but are chemically transformed into outputs, such as ammonia for fertilizers and petrochemicals that go into plastics and similar products. And also feedstocks include coke, the carbon-based fuel used in blast furnaces for reducing iron ore to metallic iron. So that's why you can have some application of CCS to fossil fuels that's referring to coke in blast furnaces, which has some potential there. But for the most part, we're looking at displacing it with either green hydrogen or bioenergy, both of which can be chemically transformed to produce those other chemicals and output products that I mentioned, or blue hydrogen, which is hydrogen formed from natural gas with carbon capture. So similar to today's steam methane reforming or in China coal gasification, but with carbon capture applied. So now we're into the graphs that show the resource requirements, which is really the heart of what this tool is about. And it's the first of these graphs is about electricity demand. Here we're looking at gray, so the historical on the left, gray is the electricity used by the rest of the economy, the non-industrial sectors, which we hold constant in this graph. And yellow is direct electricity used by industry. Green is electricity used to create green hydrogen that is used by industry. So you can see that, and then the bar heights correspond to petawatt hours on the left scale. And the red numbers are the annual growth rate if this build out were to happen over 30 years. Because of course, we wouldn't expect this overnight. The exact number of years likely would vary by region and can't be known in advance. So we're just using 30 years as an illustrative example here. So you can see that with high direct electrification, and by the way, all of these scenarios achieve zero carbon industry approximately, apart from some residual emissions from CCS. They're just using different strategies to get there. So you can see with high direct electrification, you'd need about a 2.4% annual growth rate of electricity demand over 30 years. That is reasonable. In the years from 1950 to 2023, the average growth rate of demand 0.9%. And even in recent years, 20 and 20, north of 3%, I believe. So we know the grid can expand at the necessary rate, though it definitely needs attention from policymakers to ensure that it does so. High green hydrogen requires more electricity because there's inefficiency in converting electricity to green hydrogen. And then when you burn green hydrogen, the heat is lost either in hot exhaust gases or latent heat in the formed water vapor. So the electricity demand increase is about twice as much as under the direct electrification scenario. High bioenergy, high fossil CCS don't have much electricity increase, but they have high demands in other resources, which you'll see in a moment. This is a graph of hydrogen demand in millions of metric tons of hydrogen. You can see historical there. This is only pure hydrogen. This is not the hydrogen component of blended gases like syngas formed in blast furnaces from coke, by the way. So this is what you would think of when you think of hydrogen production. High direct hydrogen electrification has a fairly modest increase, although large in percentage terms, the base is quite small, so an increase of this scale is reasonable. High green hydrogen is very large, and so on. I want to show you the next graph, which also relates to hydrogen, because it puts it in terms of hydrogen electrolyzer capacity. So electrolyzers capacity is measured in terms of the power input they would take in gigawatts when running at full capacity, their nameplate capacity. Now, this graph assumes a capacity factor of 50%, meaning that electrolyzers are running half of the time. That's the capacity factor that the International Energy Agency determined would be optimal for minimizing the cost of green hydrogen from electrolyzers. If you run the electrolyzer a lot less than 50%, you start to spread the capital costs of the electrolyzer over fewer and fewer units of hydrogen, which boosts the cost per unit hydrogen. And if you run it more than 50% of the time, if you run it 100% of the time, then you have to purchase electricity in the hours of the day when it is most expensive, and you're adding demand to the grid in the most difficult hours. So that's why the sweet spot is somewhere in the middle, around 50%. So as a matter of scale here, the total US installed capacity right now is about 1,100 gigawatts. So if they were all running at once, which, as I said, they probably wouldn't, but because of the capacity factor, but if they were all running at once, high direct electrification is about 300. High green hydrogen, though, is about 1,600, or higher capacity than is installed in the US grid today. So what if we leaned heavily into bioenergy, where we're burning it for energy, heat, and we're also using it for feedstocks? Well, gray here is the fraction of bioenergy used by the rest of the economy, for instance, to biofuel used in like ethanol. And green is used in industry. In the left-hand historical bars, I said that's primarily in the pulp and paper industry and the wood and wood products industries. High direct electrification uses bioenergy for feedstocks, a little less than half of its feedstocks, so you see an increase. The scale on the left, the fraction of agricultural land. So we have this in other units, but we think it's more intuitive to output in this unit as well. The agricultural land includes all land used for crops, all pasture and range lands used for animal grazing, and orchards and fallow land, and meadows like that. It does not include forests. It does not include lakes and mountains and urban land. That's the definition here for the percentages. So the one that's particularly challenging here is high bioenergy, which would require over 20% of the US agricultural land. That's an area of land about 25% larger than the state of Texas. And a lot of this would be converted rangelands, which would require irrigation and fertilizer and the like to turn them into croplands to grow energy crops. So there would be a lot of costs associated with this, as well as the need for all that land. It's very hard to see so much land being devoted to energy crops specifically for industrial use, or the industrial sector use, I mean. Without massive changes, the US, for example, in US diet, you could substitute more plant products for animal products, but to the degree you're seeing here, that seems unlikely, which is why bioenergy needs to be used judiciously, much like green hydrogen. This is CO2 emissions from industry. As I mentioned, all the scenarios aim for zero carbon industry, but carbon capture and sequestration doesn't capture 100% of the CO2. It captures 90 to 95% of the CO2. So you see a little bit of residual CO2 there, more in the scenario that relies more heavily on CCS. But this is a different graph looking at the use of CCS. So we have the amount of CO2 stored underground in mass units, millions of metric tons, but we find it more intuitive if you look at it as a fraction of global oil production by volume. So that's once you compress the CO2 into a supercritical fluid, it has a certain volume at the injection pressure. And that volume can be compared to the volume of oil production globally. Now, remember, this is the United States looking at and a fraction of global oil production. So for instance, in the United States, the volume of CO2 injected would be for industry, the industrial sector, uses of fossil fuels would be over 40% of the volume of oil extracted globally. And one reason this is useful is because we know how much was spent on the capital cost of oil equipment. So we can make an estimate for what the a rough estimate, back of the envelope estimate of the capital cost of CCS equipment, because it's similar to taking all the combustion from the end uses and running all of that oil infrastructure backward, compressing it, moving it through pipelines, re-injecting it down into the wells, etc. If you were to assume that the cost is broadly comparable with the cost of the equipment to move it the other way, and you get about over $3 trillion of capital investment for the high fossil CCS in the US alone, which is a difficult level of investment. Most of the others, especially the high direct hydrogen, direct electrification, green hydrogen, and bioenergy, have fairly minor CCS investments because it's focused on process CO2 emissions. And remember that this is not necessarily producing a sellable product in the end, whereas extracting oil from the ground is. So you need policy support to these investments pan out, which is why that 3.3 trillion is particularly challenging. So the Industrial Zero Emissions Calculator is not a full grid expansion model. We have a tool called the Energy Policy Simulator that will simulate power plant choice. But here, this is a simplified tool. The user inputs the share of electricity from different sources, and then it knows the capacity factors of different sources and can output the capacity. This is based on the default allocations. You can change these in a custom scenario. The findings here are similar to the electricity demand graph I showed earlier. I did want to show one graph highlighting the effects of efficiency, which is an important part of the solution. So if you check both of those boxes in the simulator for 25% energy efficiency, 15% material efficiency, we think these are very reasonable settings. For instance, all researchers at Oxford, Allwood, and Cullen found that you could achieve about 30% material efficiency while still delivering products and services with the same functionality. This setting is half of that potential. And 25% was the assumed energy efficiency improvement of the industry sector in the IEA net zero scenario over 10 years. And we are assuming this is happening over 30 years. So both are conservative settings relative to those sources. And you can see that they dramatically cut the resource needs of all resource types. But in this example, I'm showing electricity demand of the high direct electrification scenario, bringing annual growth rate down to 1.7%, which is very achievable. So the major takeaways: the direct electrification scenario in general appears to have the most feasible and balanced use of resources, given that it's using green hydrogen and bioenergy for feedstocks and such, and carbon capture for some processed CO2. Hydrogen should be reserved for high-value uses like primary steelmaking, hydrogen direct reduced iron, as well as chemical feedstocks. When you burn it, it's very inefficient because you lose energy in forming it, and then you lose energy in the hot exhaust gas and water vapor. It also creates nitrogen oxide, air pollution by splitting atmospheric nitrogen. Bioenergy use can grow to supply chemical feedstocks, but it should be provided through sustainable land use management practices. Otherwise, you might not be getting the climate benefit. For instance, if it just leads to more imported biomass from regions with poorer land use protections, you could be driving deforestation elsewhere on the globe. CCS can be expensive, And if you're using it for fossil fuel combustion as opposed to CO2 process emissions, then it's associated with upstream emissions, for instance, methane leakage from wellheads and coal mine methane processing and transport. So it's nonetheless has a role to play. It can be useful in offsetting CO2 from limestone calcination. There's others, for instance, in the chemicals and refining industries also have processed CO2. So the calculator shows that there are achievable paths forward, as well as some that are harder to achieve. Expanding the grid at 2%-ish annually, 1.7 to 2.4, depending on efficiency settings, that's less than half of the grid's historical average growth rate of 5.4% per year in the latter half of the 20th century. I mentioned that even some recent years have been 3% or higher. And then there are technological solutions, heat pumps, thermal batteries. Thermal batteries in particular are good for obtaining low-cost power from off-grid renewable energy. So not all of that demand growth has to come from on-grid resources. That's another key point. And then I've already discussed how efficiency gains can be so helpful. So thank you for taking the time to look at this. I hope you will try the Excel version and build your own scenarios. Check out the browser version. We'll have some questions right now, but we also encourage you to reach out to us at industry@energyinnovation.org. I wanted to also mention that we are working on expanding the abilities of the industry sector in the energy policy simulator. That's the computer model I mentioned earlier that model has a time series. It chooses what power plants to build based on reliability and economic considerations, and it can output impacts on jobs, public health, and much more. So if you want those types of outputs, they're coming when we finish putting these features into that tool. And of course, just to mention, we have a book out, Zero Carbon Industry from Columbia University Press, which covers an expansive view of the technologies that can transform the industry sector and the policies that could get those technologies deployed at scale. So I'm going to stop screen sharing. And I think we're happy if you want to this off and we'll take questions.
Thanks, Jeff. Thanks, Nick. So we do have one question from Eric Smith, and he asks, what drives the difference in total energies between the scenarios?
Sure, I can answer. So one of the drivers is the efficiency of converting the fuels into heat. So if you're looking at the non-feedstock energy use and you use a lot of electricity, electricity doesn't have all those heat losses from those modes I mentioned, so you need less of it to provide the same amount of heat to the finished product or material. So just comparing them in gigajoules or any other unit, you get less. The feedstocks tend to be steadier, except in regions where they're using a lot of, so feedstocks, we're assuming you can't directly electrify, and we're assuming a one-to-one replacement and on an energy basis of a fossil feedstock with hydrogen, whether green or blue or biomass. However, because coke in blast furnaces counts as a feedstock in the graphs, and we have hydrogen direct reduced iron and electrolysis pathways that can address steel making, that can change the energy in the feedstock graph. So those are the explanations for why energy use varies by scenario, even without the energy efficiency settings checked, which obviously change energy use as well.
Great, thanks. I put this into the chat, but anyone who has questions, you can either put it in the Q&A feature or raise your hand. I'll take moderator's privilege and ask both of you, was there anything surprising you found as you were putting this together? Did anything stand out to you as an interesting takeaway that you might want to share with folks?
I think for me, just the sense of the scale and how quickly the resource demands magnify for solving industrial decarbonization with some of these strategies if you lean too heavily on them, especially how magnified that happens when you're focusing on clean hydrogen for more general uses that aren't maybe their optimal application.
Yeah, I think it was similar for me. So the industry sector is large and consumes a lot of energy, including the direct use of fuels so globally, including the direct use of fuels for heat and power, direct use of fuels as feedstocks, and purchased electricity, grouping all of that, it's about 43% of final energy demand globally. And so when you're looking at decarbonizing it, the scale stands out. And so I think without a serious tool like this, people sort of have a gut feel for, oh, well, hydrogen is very useful. It can do anything. You can burn it for heat. You can turn it into chemicals. And that's true. But when you start looking at it at scale, the scale starts to become more problematic. And then this tool is what really helped put numbers to it for not just for hydrogen, all of notable as one that really stands in for literally everything. Perhaps there's a better way.
Great, thank you. We do have someone with a hand raised. I'm going to allow that person to talk. Go ahead. Sorry if I'm mispronouncing it. Suyog, you can go ahead and unmute yourself and speak. Okay, I think they have taken their hand down. We do have a question in Q&A. Are there ways to model certain policy options like a tradable or fee-based product standard or tax incentive through the EPS once the calculator has been incorporated and that module is fully developed?
Yes, the EPS has a huge array of different policy levers. One of the new ones coming, for example, is a clean heat production tax credit, which is a tax incentive, like you mentioned. There are also energy efficiency standards and carbon pricing and numerous other levers in the energy policy simulator that can apply to the industrial sector and drive energy efficiency improvements and fuel switching for new equipment. The new forthcoming version that will have all this will also be fully economically driven as well. So you can do mandated fuel switching, for instance, with electrification or hydrogen use levers, or you can let the model choose based on price-driven considerations with the cost of those fuels, which can then be further influenced by policies like the clean heat lever. So all of that is forthcoming. I mean, it won't handle every policy under the sun, but I think it will handle a broad array of different policy options, both incentives and regulatory.
Great. Thank you. So I'm not seeing any further questions, so let's give anyone one last chance to raise their hand or put it into the Q&A. All right, seeing none, just want to say thank you again to Jeff and Nick for joining. And everyone who is on this, you will get an email in a few hours with a recording as well as some helpful links. So thank you all again for joining, and we will see you soon.
Thank you all.